Well, hey everybody, welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host as always, and welcome to the podcast. Many people don't know we've been doing podcasts since all the way back in 2004 in different platforms like 1000 Mics. And we used to share them on our website called The Electrical Guru. I don't know if you remember that, way back when, like in our old time machine. But we've been doing it for quite a long time. We've helped literally hundreds of thousands of students all over the country. And thank you for taking your time to join me today in examining another important area of the National Electrical Code. But before we even get started into that, we have to do a word from our sponsor. Again, if you want some neat design t-shirts to show your pride, some coffee mugs, some phone cases. I got a neat phone case with my Tesla design on it. You'll want to check out Electrician Pride. So without further ado, let's run the commercial and get that out of the way. Today's show is sponsored by electricianpride.com. Your one-stop shop for electrician-specific t-shirts, hoodies, phone cases, mugs, die-cut stickers, leggings, and so much more. Featuring unique designs for electricians, journeymen, and master electricians, as well as electrical engineers and electrical inspectors. For more information on all the products that are available, visit us at www.electricianpride.com today. All right, thank you, and we appreciate all the support we get. All of those purchases over there does help the show, and we appreciate all that patronage. All right, so today's episode, we're going to talk about another calculation, and it does show up very frequently on exams. In fact, I know that it's on the Texas exam personally. I've seen it. I know it was there during the development stage, also when I was a part of that for the 2017 NEC for the state of Texas, and I know people have reported it in other states. It is definitely a calculation that appears on the calculation portion of an exam. And it's pretty simple to do, but it does seem to cause people a lot of confusion. In fact, I have seen people in classes and seminars when we talk about this one, they still get it wrong. So we want to, and it's really not their fault. It's how the table is written that tends to confuse people. So that's what we want to go over today in today's episode. So if you haven't guessed, we're talking about 220.88 new restaurants and a calculation using tables 220.88, which is an optional method under Part 4 of Article 220. Now, first thing I want to get out of the way is most of the time when you see these optional method calculations, you have to know that you can use Part 3, which is a standard method. In reality, people don't use Part 3 simply because of all the steps and everything that's involved in it. So they want to say, well, I want to use the optional method. Now, of course, with using the optional method, you have some caveats to that you have to accomplish in order to be able to use the optional method. Okay, you have to validate your installation can comply with using this optional method. So that's what we're going to do first. We're going to look at the concept of when can I use this optional method for a new restaurant, and when do I use a Part 3, which is a standard method in Article 220. Okay, so let's read what it says in the code so that we can actually analyze it and break it down. It says, and hopefully you've got your code book, and I'm working out of the 2020 edition of the National Electrical Code, the electronic edition. You can use the 2017 or the 2020 because this did not change for the 2017 to 2020 code cycle. So it's intact. Nothing's changed, so it wouldn't throw you if you used an earlier cycle than the 2020. All right, so here's what it says. It says, calculation of a service or feeder load where the feeder serves the total load for a new restaurant shall be permitted in accordance with Table 220.88 in lieu of Part 3 of this article. So this is directly giving you permission to use the optional method in lieu of the more complicated, in my opinion, standard method. Now, caveats. Obviously, you can do it for services for the new restaurant, but what about the feeder? Now, you notice that it says for service or feeder loads, but then it immediately says where the feeder serves the total load. Now, a couple of cycles ago, we used to call this the power feeder or the main power feeder. And so we removed that reference to main power feeder a couple cycles ago. And so it makes it harder because now us educators have to actually explain what we're talking about. So let me talk about when it says serve the total load. Here's what it means. So let's say we have this restaurant and we have service equipment in this restaurant. And we have service conductors coming in from the utility into this panel. Now, if it comes into this panel and then this is the final destination of those service conductors, and now I've got multiple feeders coming out to other panels or potentially branch circuits going out to other panels, then I can do this. I can use this optional method for the service load calculation, but I can't use it for any of the subsequent feeders that are coming out of it. Why? Because those feeders, there's more than one, and they're serving other loads, so those feeders are not serving the total load of the restaurant. Okay, makes sense? So what would you size them? Well, you would size the panels that they're maybe feeding based on part 3 for whatever the loads that are in that panel, and subsequently that's going to how you size the feeder conductors, right? Based on the load that's in that panel, the load being served. However, the scenario where I can use this optional for a feeder goes a little different. Let's look at that same scenario again, and you'll see crystal clear when you can use this optional method. So we come in with our service conductors, and we feed a main service disconnect, okay, at this restaurant. Now, the reason we're hitting this main service disconnect because the owner wants the actual additional branch circuits and other feeders or whatnot to be from a panel that's located more centrally located in the restaurant, down further into the restaurant. Well, we know that we're limited on how far service conductors can come into the building based on 230.70A1, right? Outside or nearest point of entry. So that's why we put this service disconnect up. Now, that's just a service disconnect. On the load side of that service disconnect, and there's no other loads being served out of that service disconnect except for the feeder that's feeding a remote distribution panel downstream, just like the owner wants. Now, that is a feeder. But since all of the loads for the actual restaurant are going to be coming out of that downstream remote distribution panel, that feeder that's coming from the service disconnect to that downstream remote panel is considered a main power feeder, even though we don't define it as that anymore. That feeder is seeing the same loads as the service conductors are seeing. If that's the case, then you can size that feeder or determine the loads for sizing that feeder based on this optional method. Okay? Another thing to remember is in that scenario, that feeder never has to have a greater ampacity than the service conductors. Well, that makes sense, doesn't it? Because what would be the point? Why would you want the feeder to have to be larger than what you calculate for the service? It doesn't. So again, that's written into the rule in 220.88 for clarity. Now, also, it reminds us that any of those feeders that are coming out of that remote distribution panel, because you can have feeders out of there as well, those would be sized based on part 3. Okay, so again, that would be something that you would use the standard method to do. You could not use this optional calculation for that. Okay, all right, so let's bring it back now. So we moved beyond that. We kind of got a good understanding. Now let's talk about overload protection. Now, service conductors that come into a service enclosure do not have short circuit and ground fault protection. Okay, but they do have overload protection. And that's in accordance with 230.90 and meeting rules at 240.4. And so we have to make sure that we're protecting those service conductors from an overload condition. Now, be honest with you, all panels that are service panels, when you come to the main breaker or you hit the main breaker, everything upstream is coming from the secondary side of a transformer. Yes, it might have it's going to have some protection on the primary side, probably not on the secondary side. We don't concern ourselves with that. All we want to do is make sure that we're protecting those conductors from an overload condition. We certainly can't protect them from a short circuit and ground fault protection because that's going to be downstream of the overcurrent protective device. Okay. So again, and this also begs us to make sure that we define what an overcurrent protection is. That is short circuit, ground fault protection, and overload protection. But of course, we can't provide the short circuit and ground fault protection to service conductors. But we can protect it from overload. Okay, and that's what's given to us in this requirement. And it sends us and tells us about 230.90. And in 230.90 is when it talks about having the overcurrent protected device in series with each ungrounded conductor. And it talks about the fuses and the sizing, and it can't be higher than this and that and all that. So you can have and it also says each ungrounded service conductor shall have overload protection. Okay, and of course, then it goes on to have an A and a B and talks about overcurrent devices in series with each ungrounded conductor. It has a rating or setting not higher than the ampacity of the conductor and yada, yada, yada. Okay, so you get all those things. Of course, you do have some exceptions to the general rule, but just wanted to kind of tell you that you're going to have to protect those service conductors. We know that. You know that. And then, of course, we don't want to forget 240.4, which is protection of those conductors. You have to protect the conductor at its ampacity, okay, against overcurrent. But you have all the rules in 310.14 that you have to meet as well, which is adjustment and corrections and everything else. But it also, remember that this is where we get the infamous 240.4b, whereas if it's 800 amps or less, the next standard overcurrent device rated shall be permitted to be used. Again, this is where you would have, let's say, a conductor that's rated for 37 amps could be protected by a 40 amp breaker, and it would be okay. All right? But you have to meet the caveats, and there's 3 caveats there that you need to be aware of. And we're not going to go into those, but just a reminder that you can only protect service conductors for overload protection. Okay? All right. And of course, we talked about the feeders not required to be a greater ampacity than the service conductors. Again, that does not apply in our scenario where we didn't have a main power feeder, whereas we had a remote distribution panel that ultimately downstream had multiple feeders coming out of that. Incidentally, they would never be larger than the service conductors anyway, so that's kind of a moot point to even discuss. They're going to be sized based on whatever the calculated load is for the panel that they're supplying or the equipment they're supplying. Okay, goes without saying, right? Okay, now, when it comes to sizing the neutral loads, the code also reminds us here in 220.88 that if you're going to use this optional method, that you still would size your neutral are permitted to be sized in accordance with 220.61. Now, what's significant about that is that you know that you can't size neutral conductors based on an optional method. So without this reference back to 220.61, which incidentally appears in part 3, which is a standard method, you get to go back for neutral and follow all those rules for neutral, which ultimately means you're basically going to size the neutral conductor based on a standard calculation. This is why I teach people to understand the standard method and the optional method. You really need to know how to do both in order to be able to use. Now, the beauty is usually people do the standard method and it results in a certain size service, and then they say, well, let me compare it to the optional method. And then if the optional method ends up being less, then that's what they use. But you're still going to size the neutral to the standard method. Okay? So again, that's how we teach it. Teach you the standard method in an understanding that you have the option by permissive rules to use the optional method. Okay? So there's a lot of times there's people out there that say, don't worry about the standard, just go to the optional. Not the way to be. You should not have that kind of mentality in your head. You need to know how to do a standard method. And the optional methods are always going to be a little easier to calculate. Okay? But you need to learn the standard method for everything. Okay? Especially if you're going to size neutrals and things like that. Now, let's get on to the table. So what you've got here is a table 220.88, which is an optional method. It's a permitted load calculation in lieu of Part 3. And so this is for service and feeder conductors for new restaurants. Okay? So you've got 3 columns here. You got total connected load, you got all electric restaurant calculated loads, and you got not all electric restaurant calculated loads. Now, up front, I'll tell you a couple things. If you're ever in an exam, and I'm just saying this for those that are preparing for an exam, you'll see the terms connected and calculated. Connected means the total loads simply added up. And the calculated is the calculated value after you apply some type of calculation, whether it's percentages, people call it demand values. Once you get a value after that, that is your calculated load, means you had to do something. The connected load is simply taking all the loads. Now, the reason I bring that up is because a lot of times on exams, they might ask you, what is for like say a single family dwelling, they might say, what is the total connected load for the general lighting circuits? And when they say general lighting, they might say general lighting and general use receptacle circuits. Okay, if that's the case, then many times what they're trying to do is simply try to find the 3 VA per square foot, 2 small appliance branch circuits, and 1 laundry, both of those, all of those being 1,500 VA for the 2 small appliance, 1,500 VA each, in a laundry at 1,500 VA. Adding everything up, depending on how they ask the question, that would be a connected load. Whereas if you apply the demand factors in 220.42, which is where you get, again, remember the first 3,000 at 100%, 3,001 to 120 at 35%, and anything over 120 at 25%, those are demand factors. Once you apply those, then you get what's called a calculated load. And so it depends on how they ask the question. You might be simply adding up the loads to give them a connected load value. But if they say, give me the calculated load, then you know that something's got to be applied, like demand factors. You're looking for some solution. You're going to have to work some math, if you will. Okay? So it's kind of a little tip based on whether or not they make a reference to connected versus calculated. And that has never been more evident than when you look at table 220.88, because it specifically says, what's the connected load? It's adding everything up. What is the calculated load? A value that you're going to achieve after you do a calculation. Okay? Now, before we even get started in this table and analyzing it and giving an example, I want you to read the note, because the note is extremely important. It's kind of telling you how you come up with that total connected load is what we're working with here. Now, for an engineer or designer, it is literally adding up all of the luminaire outputs, all of the appliances, everything up in order to come up with a total connected load. Okay? You're literally adding everything in. So what does it say? It says, note, add all electrical loads, including both heating and cooling loads, to calculate the total connected load. Select the one demand factor that applies from the table, then multiply the total connected load by this single demand factor. Okay? Now, the other thing that's kind of misleading is it's not so much how they wrote it, because I guess people get misled. You could have probably left that last part off and it'd be pretty intuitive. But we're going to work through an example. Okay? Now, our example, let's say, is going to be, we know that we have a total connected load of 450 kVA. Okay? So that's what we've got. We're going to work our example. We have 450 kVA. Okay? So 450,000 VA. Now, once we establish our total connected load, which is either provided by the engineer or you literally added up all the electric loads in this building, every one of them cumulatively. And then you go to the first column. And we're going to go down, and we go down to column. It's going to go down to the third one. So it's between 326 and 800, because that's what our kVA is. We had 450. Falls right there smack in the middle here of these. Now, in our case, we have an all-electric restaurant. Now, don't get lost in the semantics of whether it says all-electric or not all-electric. If it's all-electric, then everything in there is electric. If it's got gas ranges or gas ovens or whatnot, then you're going to simply go to the not all-electric, because it's not all-electric. Pretty simple, right? It's not all-electric. So, again, the question on an exam is going to tell you whether it's all electric or not all electric. Or what they might say in an exam is you have a new restaurant with a gas range. What is the load calculation for the service using the optional method? And immediately in your mind, you're like, well, there's a gas range. It's not all electric. Boom. Okay. Now, the other thing in that question is they got to give you a value, because they're not giving you enough information to do the calculation. You don't know what all the loads are. So they're going to say you have, like in our example, they'll say it's a 450 kVA a new restaurant, and what is the size of the service conductors based on the optional method. Now, in that scenario, they didn't tell you there was anything that was gas, and so you assume it's all electric. Okay, so you have to slow down, read the question. Once you establish whether it's all electric, focus on that. If you establish that there's something in there gas, and you're not going to assume it, they have to tell you, then you're going to focus on the not all electric. But in our case, it's all electric. So it's 450 kVA, so we're in the third one down from the left side, and that's 326 to 800. Now let's go to the right. And here's where people get confused. They will take that 450, and they will do it at 50%, and then add the 172.5. And that is not the way to do it. And probably 8 out of 10 people do it that way because they don't understand the concept of work parentheses first and then solve your problem. So what you see here is it says the amount that's over 325. Well, in our case, it was 450. So we take 450 and we're going to take away 325. That gives us 125. So the 125 is the amount that is over 325 based on our 450 kVA value. Now, once I have that 125, then you come outside of the parentheses and you work the math. It's 50% of that 125. Okay? So 125 times 50% is 62.5. So 62.5, then you add the 172.5 plus 172.5 is 235 kVA. And that's what I'm going to use. Again, if it's a 122 40 volt restaurant, then I'm just going to take that kVA. I'm going to divide it by 240, and then that's going to tell me what my service needs to be. That's going to help me size my conductors. Okay, you get it? So a lot of people get this confused. Now, if it's not all electric, it's no different. Because I can tell you right now, if it was 450 kVA all electric, the not all electric is going to be less than that because you're taking away some of the electrical load. Okay? So, again, you just simply follow the same math. Again, solve the parentheses first, okay, and then apply the percentage to that value, and then add the additional kVA that's out to the right, all right? And I think you'll see that that will be an easy calculation for you to be able to get right on an exam. And to understand it in the real world. Because if you're a restaurant's being done by an engineer and you're the electrician, all they're going to do is give you a total connected load based on everything that they put in this building. The lighting, the total amount, everything. They're just going to give you a total electrical load that is the total connected load value. Okay? They're going to give you this value. And it's pretty simple at that point to choose whether or not it's an all-electric restaurant or not all-electric restaurant. And if it's an all-electric restaurant, then you do just like we did, determine the amount that is over whatever's in the parenthesis. In our case was 450, so it says the amount over 325, and it was 125 is what is over 325. That's the difference between 450 minus 325, so we can find out what that specific amount is that's over 325. Then you take that value at 50%, and then you add the 172.5 onto it. Okay? Makes sense? All right, so that's how you work it, and that's how you do a new restaurant under 220.88, and hopefully that's been pretty simple for you. I tried to break it down and keep it really simple, not complicated. Don't go outside of the realm of the optional method. For on an exam, they're going to have to give you the connected load, okay? But even if they don't, it's pretty simple. You're simply adding up all of the connected loads, okay? All of the electrical loads, taking them at face value, plus the heating and the cooling to get your total connected load. Basically, you're dumping everything into the pot, and you're adding it up, and you get to do an overall demand factor on it. It's a beautiful thing. So hopefully you got something out of that. If you have any questions, feel free to email us at info, that's INFO, at masterthenec.com. That's MASTERTHENEC NEC.com, or you can just visit our websites at masterthenec.com or electricalcodeacademy.com. And up at the right corner, you'll see a Contact Us button. You click on it. You can send us an email from our internal system, and we're more than happy to comment on it or give you some feedback or help you out any way we can. If you're looking to learn the National Electrical Code more, then check out our courses. We have some of the best courses in the industry. If you're preparing for an exam, our Fast Tracks program is beyond compare. You will learn the code and everything you need to pass the exam, but also become a better, well-rounded electrician. But of course, we also have our residential, commercial, industrial, grounding and bonding courses as well that are also now available over on the Electricians Academy, I should say that, at electricalinstructor.com. So we have many ways to reach out to us. Thank you for listening over on our YouTube channels. Make sure you subscribe to our YouTube channels, our Twitters, our Facebooks, and whatnot. We appreciate you. Till next time, stay safe.